In this lecture, we're going to look at something called fuel cells. Now, fuel cells are electrochemical cells that produce electrical work from oxidation of hydrogen. Now, fuel cells are very commonly used on spacecrafts. They provide electricity to the various appliances found on spacecrafts. So let's look at the oxidation and reduction reactions found in a fuel cell. So our oxidation is as follows. A diatomic hydrogen is oxidized and it releases 2 H plus ions and 2 electrons. Our reduction reaction is as follows. A diatomic oxygen molecule takes up those 2 electrons and also takes up the 2 H plus ions, forming water in a liquid state. Now our net redox reaction is found by simply adding up these guys. We see that the H2 plus ions cancel, the electrons cancel, and we have the following redox reaction. Now our E is 0.7. Our cell potential for our fuel cell is 0.7 volts. It's positive. Now let's look at the layout of a fuel cell. A fuel cell, like any other electrochemical cell, has an anode and a cathode. It has a conductor that carries electrons from the anode to the cathode. And this is our outside system that receives electricity in the form of moving electrons. Now, like always, or like most cases, our anode is negatively charged and our cathode is positively charged. And that's why electrons travel from the negative charge to the positive charge. Now, inside our anode, we need to allow H2 molecules in the gas state in. And that's why we have an outside power source that allows those H2 ions or H2 molecules inside our anode. And to make sure our pressure is not increasing, make sure there's no buildup in pressure, this needs to be released back into some outside location. That's why we have this guy on the bottom. So, when this H2 molecule enters our system, it is oxidized. But how is it oxidized? Well, this brown little layer is a platinum catalyst. And this platinum acts to catalyze or speed up the reaction going from our reactant to products. So when this guy enters our anode, it reacts with the platinum catalyst, producing 2 moles of H plus ions and 2 moles of electrons. Now these 2 moles of electrons travel via the conductor this way. Notice we have a membrane, and this membrane does not allow our electrons to pass from this anode to cathode via this membrane. This membrane only allows H plus ions to flow, or protons to flow. Now, why should we allow protons to flow? Well, we'll talk about that in a bit. But notice some of the H or diatomic H must leave because we can't have a pressure buildup in this system. So now we have the 2 electrons traveling all the way to this cathode. Now when it travels through this guy provides electricity to some outside source. This is where the electrical work is done. Now, when this electron or 2 electrons travel all the way down to this cathode, these electrons react with the oxygen molecule, reducing it. But notice that in order for this buildup of H plus ions not to occur, these H plus ions must pass to this side. So this, in a way, acts as a salt bridge. Because if this membrane wasn't here, we'd have a buildup of positive charge here and a lack of positive charge here. And then that means our electrons would stop flowing. So to close the circuit, we need this membrane. And so these H plus ions travel from the anode to the cathode. And when they reach this position, they react with the oxygen and the electrons, forming water. Now this water needs to be released somewhere, because if the water remains, there's a buildup of water and our cell would eventually stop functioning. So this water leaves through some outside pump and is stored somewhere else. Now notice the same way we need to allow H2 molecules inside our anode, we need to allow O2 molecules inside our cathode. And that's why we have this guy here. When this oxygen enters the cathode, it reacts with the H plus ions and electrons coming in, and it forms our water. And this is a continuous process, and it powers some outside source in this area here. So we have a few problems with our fuel cells. The first major problem is diatomic H2 molecule does not occur in nature, and it's very difficult and takes a lot of energy and money to generate it. So it's very, very expensive, and that's why places like NASA use it. So it's probably a very bad idea to commercialize it because of its expense. The second issue with H2 in the gas state is that it's very flammable, and that means it's very difficult to store.